All right, we finally got everything up here in class. You're gonna have to kind of scramble and think about what I want to do today. So I think what we're gonna do, I was gonna do some Excel stuff. I already have a video of that recorded elsewhere, so I might just post that. It'll be about 30 minutes. So let's get this pulled up here. I'll kind of show you. Whoop, it's not what I want. All right. So I think last class we left off kind of like here, and I said we'll start with some Excel next class. Like I said, I think what I'll do is I'll post a video of that on YouTube, so it'll be separate from today's like recorded lecture, since we lost about 30 minutes. It's basically me going through and showing you how you would build a contingency table of your own in Excel. So we've done all this work with these contingency tables. Where did these probabilities come from? Well, they came from some data set, and we can actually construct them. All right, so I'll post that video up on YouTube. We'll have kind of after this week in Excel, another, the second Excel assignment. We'll have part of it will be related to building your own contingency table. So you'll have to kind of get on and watch that at some point. I apologize for the, like I said, for the inconvenience of this. Hopefully we won't be dealing with it moving forward, or we'll be in a different classroom. So where we left off, in terms of the kind of theory, the statistics side of it as opposed to the Excel, we had these three rules. So we had this complement rule, which was that the complement of an event is 1 minus the probability of that event. We have this addition rule, which told us we can find the union of two things by adding up the probability of each event and subtracting what we double counted, which was that intersection. We then had this multiplication rule, which was the intersection of two events can be solved for by taking a conditional probability multiplied by the probability of what I'm conditioning on. Okay? So we're going to use all of these things. We're going to set up our next topic. This is kind of what the last Learn Smart should have had some information about. So hopefully some of this you've seen before. But basically, we're going to have this thing we call Bayes' theorem. And the general idea is that you start out thinking that there's a probability of an event. You see some additional information, and then you update that probability, right? So this would be like, I think that it's impossible, maybe, I don't know, for somebody to, jump, 4 or 5 feet up in the air, whatever height I'm thinking about. So I think the probability is 0. I then see somebody do it. Well, I now have to update my probability. I still think it's probably very unlikely most people could jump that high, but I've seen someone do it, so now my probability has to be something other than 0, right? So we're just updating our probability based off the outcome of some experiment or some test, okay? So the types of scenarios where we're going to be setting this up is that we have two underlying states of nature, okay? So call this S1 and S2. These are the only two things. So this would be something like, I think you have the examples here. Someone is, right, either guilty or not guilty of a crime. Not what the jury finds them, but the underlying state of nature is that they are in fact either guilty or not guilty, right? Someone is either lying or not lying to you. Someone does have HIV, or we can think about kind of COVID here, or pregnant, not pregnant, right? There's only two outcomes for this state of nature. You're either in state of nature 1 or you're in state of nature 2. Now, we can't, like with our eyes, directly observe this, right? Oh, sorry. So, sorry, if these are the only two things that exist, we can think about the probabilities have to add up to 1. Right? If I take the probability somebody is guilty plus the probability they're not guilty, those are the only two possible outcomes, so those have to add up to 1. Right? So we don't know what the true state of nature is, so we're going to run some tests, right? And we're going to say that there's two outcomes for the test. We'll call this E and E complement. Usually, this is something like, it's either test comes back positive or negative for a certain disease. We can think about a jury comes back with a guilty or innocent finding. Right, we'll set this up in a couple different examples, but we're looking at some outcome of a test based off of whether or not we see, what the outcome of that test is, based off what we see. We'll then update the probabilities of the underlying state of nature, right? If someone in front of me just says, what's the probability that I have, currently have COVID? Well, I don't know. It's relatively, what's the percent of the population that's had it at this point? So I might give it roughly that. However, if you tell me that, well, now this person tells you that they just took a test and it came back positive, well, now I think the probability they have COVID is probably a lot higher, right? Now, it could be a false positive, so it's not a 100% likelihood, but I'm going to update my probability of those states of nature based off of the outcome of the test that I saw, okay? And I think I had from the last slide here, I might have moved some things around so this doesn't make sense. But in general, what we're saying there is then, okay, given that I see some outcome on a test, what's the probability that this is the state of nature, right? Given that I saw the test came back positive, what's the probability somebody actually has COVID? Okay. I think I had it phrased as HIV, kind of positive or negative here. You can kind of think about this as, you know, any disease really, right? What we're thinking about, you either have it or you don't. Okay. So usually what we would like to do is start out with a conditional probability. We can rewrite that as the intersection of those two events and then divide by the probability of what I'm conditioning on. Now the problem is, if I think about this here, if E is the outcome of the test, what's the probability that someone just gets back a positive test? Well, it kind of depends on what that state of nature is. So it's very unlikely that I'm going to have just the probability someone gets a positive test result without any other information, right? So we can break this down, and in certain situations, we're only going to have the information that we'll have does not allow us to directly just plug in two values here. But we can break these down. So this intersection of the two events, I can then rewrite as kind of the conditional probability times the probability of what I'm conditioning on. Right? So if I want to break this down even further, right, I've got this conditional probability times the probability of what I'm conditioning on, the probability of E. Well, I can break that up into what's the probability that someone gets a positive test result and has the disease, plus the probability someone gets a positive test result and doesn't have the disease. Right? Those are the only possible people who come back with a positive test result, right? They either get a positive test result and they have the disease, or they get a positive test result and they don't have the disease. So, we're going to break up that probability of E into these two intersections. But I then know I can rewrite the intersections here as conditional probabilities times what I'm conditioning on. So really, it's just a little bit of math. Once we have that, we're just kind of substituting in for these intersections the equation of a conditional probability times what we condition on. Notice here, they're different states of nature. So when we write that out, one of these will be conditioning on state of nature 1. One of these will be conditioning on state of nature 2. Okay. Once I have that, I can plug that in for the probability of E down here. And then the intersection I can rewrite as the conditional probability times what I'm conditioning on. So we don't have to know kind of all the math here, but basically we're starting out here, and with substituting things that we know, we can arrive at this equation. So this is what we call kind of Bayes' theorem or Bayes' equation. So I want to try to give you kind of an intuition behind what the components in this equation represent, right? So if I'm thinking about, if I see somebody gets a positive test result for, we'll say, having HIV, because I think that's what the slides have, what's the probability they actually have it, right? So given that I see a positive test result, what's the probability that they actually have the disease? Well, first of all, if I see someone get a positive test result, there's going to be two types of people in that category. One, somebody who has the disease and tested positive, right? It was a correct positive test. But two, people who didn't have the disease and got a false positive, okay? So really, anytime you see a positive test result, some of those people will actually not have the disease, right? Now, hopefully, if these tests are accurate, right, there won't be as many people who had a false positive than there are got a true positive. So what this denominator represents, you can kind of see that there's two groups here, right? And originally, those were the intersections of, did I get a positive test result and have the disease? And did I get a positive test result and not have the disease? So essentially, this denominator is looking at the total number of people who got a positive test result, right? Some of them didn't have the disease, some of them did. Well, then if I want to think about, given that I've seen a positive test result, what's the probability someone actually has the disease? Well, I'll take the number of people who got a positive test result and had the disease and divide that by just the number of people who had a positive test result, right? Which that group is kind of composed of two different types. Right? Now, I'm talking about these in terms of numbers because I think it's a little bit easier to think about it that way, right? Let's say, 100 people take the test, right? And 10 people who had the disease got a positive test result. And then we had 10 people who didn't have the disease who also got a positive test result. So maybe this test is really good at identifying people with the disease, but it also has high false positive rates, right? So if I were to take those 10 people who got the positive test result and had the disease and the other 10 who got a positive test result but didn't have the disease, that gives me 20 total people who got a positive test result. So now if I see a positive test result, the probability that the person actually has the disease, only 10 out of those 20 actually had the disease, right? The other 10 were the false positives. So now if you tell me that given that I see a positive test result, the probability someone has disease is only 50% or 0.5, right? And that's the issue if we have a test that has really high false positive rates. Then seeing a positive test result starts to have less meaning, right? If the false positive rate is 90%, that 90% of people who don't have the disease are still getting a positive test result, well, that's a problem, right? The positive test result doesn't tell us anything. So that's the idea behind this equation. And I talked about it in terms of numbers, but really what we're going to do is base this off of probabilities. But we talked about, going back to histograms, and I'll go over this a little bit more in that Excel kind of video. But to get these probabilities, all we're really doing is taking a frequency and dividing it by the total number of observations. So anytime we're dealing with probabilities, intuitively, we can still think about this as like numbers, frequencies, right? Because we've just gotten these probabilities by taking frequencies and dividing by the total number of observations. And you kind of can see where I was plugging things in. I try to keep them the same color here, but like I said, I'm not going to ask you ever to reproduce this. So let's think a little bit more about some of the properties that we can use to solve kind of some of these Bayes' theorem examples. So I already told you the states of nature, those probabilities have to add up to 1. I think this makes sense, right? If I say the probability somebody has blue eyes plus the probability somebody doesn't have blue eyes, that has to add up to 1, right? That covers every single possible outcome. That one's not too bad. So this one's a little bit different, right? If I condition on the same state of nature, right? The probability of the two outcomes of the test have to add up to 1. So the idea behind this is that if I'm saying I'm going to condition on, say, the people who have the disease. If I were to look at my entire group and then I then said, okay, I'm going to limit this down. I'm going to condition on only looking at the people in this room who have whatever disease I'm looking at. So it could just be HIV, it could be COVID, right? Once I'm looking at that smaller group of people, well, those people either get a positive test result or they don't, right? They get a negative test result. However, those are the only two outcomes if we're kind of ignoring kind of any inconclusive like tests here. So I either see that group of people, if I'm conditioning on the same state of nature, the probability they get a positive test result plus the probability they get a negative test result, those have to add up to 1. Okay? So I left this kind of as S subscript I because it doesn't matter what state of nature I condition on, state of nature 1 or state of nature 2, as long as I'm conditioning on the same state of nature, those conditional probabilities for the two outcomes of the test have to add up to 1 as well. Right? I don't think that's too bad. Now, if we start to condition on different states of nature, the probability of the outcomes of the test don't have to add up to anything. Okay? That could be, actually, in fact, it could add up to over 1 because it just doesn't make sense what we're doing there. But it's easy to make that mistake if you forget that you have to be conditioning on the same state of nature here, right? S1 and S2 aren't the same state of nature. And when we actually start writing these out in the kind of verbiage of our examples, this makes a little more sense because we can kind of see like it's not S1 and S2, it's like an actual word, so it's a little bit easier to identify that we're making sure we condition on the same state of nature here. Oops, sorry. So with this in mind, I'm going to kind of walk you through an example. And And we'll use HIV test data because I had some information on that. I think maybe on Tuesday, I'll bring in something where I look at some recent COVID data. I had some old data on the test. I think it might be in the slides, but I'll try to update it. So if I go and I'm thinking about whether or not somebody has HIV, there's only two outcomes, right? They either have it or they don't, okay? So here, the probability that somebody has HIV, we could call this state of nature 1, is 0.006. If I just selected a person at random in the US, okay? However, the tests are pretty accurate. So if someone has HIV, right, they actually are HIV positive, given that they're HIV positive, the probability that we see a positive test result, right, is 0.999, right? So these tests are pretty accurate. If somebody has the disease, the test identifies it 99.9% of the time. Okay? And I'll kind of write out what these, actually, let me see if I can, let's try something a little tricky here. There we go. Oops, go back here. So really what I'm thinking about here is the very first thing I was given, and I'll kind of zoom in on this and show a larger. Is that okay for you guys out there? Can you read this? All right, I'll say I can make it larger here in a second. What we've really said is the probability that someone is HIV positive is 0.006. Right? What's the probability then? It wasn't directly given this, but what's the probability somebody is HIV negative? These are my two states of nature. Let's call this S1 and S2. What do those probabilities have to add up to? 1, right? So if the probability of this state of nature is 0.006, this one has to be 1 minus that, or what, 0.994? Okay. Now the second thing I was given, right, the probability an HIV test records a positive result for a HIV positive person, what we're really saying there is given that the person is HIV positive, the probability that the test shows a positive result, sorry, this is supposed to be a positive sign, that's pretty bad, right, was 0.999, right, or 99.9% of the time. So this is where I said, you know, if we're thinking about, if we're conditioning on the same state of nature, so remember this is S1. If I condition on the same state of nature, HIV positive, S1 I was going to write up here, right? So given that the person has HIV, the probability they get a positive test result is 0.999. So what would the probability be that they get a negative test result? Those are the only two test outcomes I could see. This should be what? Someone's probably blowing the chat up with it. Hold on. Yeah, 0.001, right? Oh. Yeah, we can. Okay. Oh, I almost lost it. So if we condition on the same state of nature, right, I can only see a positive or a negative test result. So those probabilities have to add up to 1, right? So when I knew the one was 0.99, I automatically knew the other was 0.001. So we really only given directly these two probabilities, but we could infer what these other two were, okay? We then have kind of the last thing, which is the probability an HIV test records a positive result for someone who's HIV negative is 0.01. So what are we really saying there? I thought I could make this a little bit bigger, but maybe not. It's as big as it goes. So there, what we were given is that given that somebody is HIV negative, or state of nature 2, the probability that the test comes back positive is 0.01. Which means that if I condition on that same state of nature that someone is HIV negative, well, if the probability they get a positive test result is 0.01, the probability that they get a negative test result should be what? Just, yeah, 0.99, right? Those are the only two possible outcomes. I'm conditioning on the same state of nature. Okay? So I now have all the probabilities I could need to kind of solve that Bayes theorem problem. So we'll work through that here in just a second. Okay? But before I move on, everybody okay with this? Any questions on this? We're okay? All right. So keep these in mind. But the question that we have is if a test was administered at random and the person comes back and the test comes back positive, what's the probability they actually have the disease? So what we're really looking for there is, given that the test result we see is positive, what's the probability the person is HIV positive? Okay. So that's what we're looking for there. Now, I'm thinking about this is my state of nature, and this is my outcome of the test E. Okay. So, I'll come back to that in a second. I'm going to minimize this. So this is what we're looking for right here. I'll pop this back up on the screen in a second. So this was like all the information we were directly given. I worked through everything that we could have inferred some other probabilities from these things. But these are just the ones that we are directly given. Here's what we were looking for. So the probability I get a positive test result, what's the probability the person actually has HIV? So I'm just going to write out the formula in the context of my example. So I did that here, right? And I guess I forgot how I denoted this, but here where I'm writing P0 or POS, which was an abbreviation, I just was thinking about this as the test result comes back positive. It just is a shorthand, just depends on how you want to write that. So basically, we're looking for this. And I'm just going to go back. Maybe I can minimize this. There we go. I'm going to go back to that general equation that I had right here. I'm going to write everything out in the context of my example, where my E was seeing a positive test result, and my state of nature I was interested in was if the person actually had HIV. Okay. So that's all I did was I took that and I wrote that equation out in the context of my example. Okay. So now it's really just a matter of plugging things in. Right. When I wrote down everything that we had initially, we had the probability someone is HIV positive, 0.006. So everywhere I see this probability of HIV positive, I can plug a 0.006 in there. Probability someone's HIV negative, we had that was 0.994, so I plug that value in. Given that someone's HIV positive, what's the probability they get a positive test result? Well, that was where? Right here. So 0.999, plug that in for those two. And then given that someone's HIV negative, what's the probability they get a positive test result? That would be 0.01. So once we've identified those probabilities, it's really just writing this out in the context of our example and plugging in all those values. Okay? Any questions on that? Also, if you're on Zoom, because I think it depends on how you want this to display. I'm sharing my screen, but I'm also at the same time kind of showing you what's on the dot cam. So if you have the video minimized, you would want to have that pulled up on the side as well. So it'll be fine in the recorded video and for you guys here in class, but if you're on Zoom, you want to have that video pulled up as well. So, really, it's just a matter of plugging all those values in, and then it's just getting that entered into our calculator. Okay. Now, this is kind of a weird one because given that I see a positive test result, the probability the person actually has HIV here is only 38% or 0.38. So why is that so low, right? You would think a positive test result should, and I even mentioned earlier, these tests are really good at identifying someone if they have the disease. The problem is we've got two groups of people, remember. One who have the disease and get a positive test result, and one who don't have the disease and get a positive test result. Okay? So if I'm thinking about maybe taking these probabilities and thinking about what this would be like in terms of numbers, I'll try to give you an idea about where this is coming from. Oh, wait. There we go. I really thought I could make this a little bit bigger, but I guess not. So, get this to focus. Let's think about these probabilities in terms of United States numbers, right? So here was the probability someone was HIV negative, right? So 0.006% of the United States population has HIV. I'm going to use a rough number that there's 300 million Americans. I know it's higher, but that makes our math a little bit easier. So let's say, even if this wasn't, so let's say this was, it's a little bit above it, but let's say it's about 0.5%, okay? So 1% of 300 million would be 3 million people, 0.5%. That probability of 0.006 is really kind of representing 1.5 million people, right? Of those 1.5 million people, 99.9% of them, we pick up with a positive test result. So I could multiply this by 0.999, but really roughly, the number of people who have HIV and get a positive test result is 1.5 million, right? So these are people that are getting a positive test result and HIV positive. This was supposed to be a set symbol and. Right? This first part of the denominator is actually representing that same thing. So the denominator, remember, represents just the total number of people who get this positive test result. So the number of people who get a positive test result but don't have the disease, well, 99.4% of people don't have this disease, right? So really, instead of 1.5 million people have it, we're thinking about there's what, 298.5 million people that don't have the disease. And about 1% of them will get a false positive, right? So if we're doing a roughly 1% of this large value, this is going to be approximately what? I mean, a little bit under, but we'll call it what, 2.985 million, just a little bit under 3 million. Just for the sake of the example, we'll call this 3 million, right? So these are people who were HIV negative, but they got these false positive test results. So now if I think about what's going on, I've got 1.5 million people with positive test results who have the disease, but I've got 3 million people who don't have the disease that got a positive test result. So now if I'm thinking about my group of people who got a positive test result, there's 4.5 million of them, and only 1.5 million, oops, I'm off the screen, actually have the disease, right? So that's why when I see a positive test result, the probability they actually have the disease was as low as about 38%, okay? And that's because, these false positives, yeah, 1% doesn't sound like a lot, but if the majority of the country doesn't have the disease, 99.4% of people, 1% of false positives will be just a large number of people, right? 1% of 300 million is going to end up being larger than 100% of 300 million, right? So it just ends up being the way that the numbers work out here. And this typically is the case when we have very skewed states of nature, right? Here, 0.006 versus 0.994, as opposed to something like, 40% have the disease, 60% don't, right? Then we might not end up with something quite as crazy. So I don't know. I like to just kind of give some numbers, kind of hopefully thinking about, yes, these are probabilities, but we really can think about it. They represent a number of people. If we were just to multiply them by like the total number of observations, or the way I did in this case, right, the total number of Americans, right, because that was our population, okay? All right, any questions on this so far? We'll do some more examples, but, okay. Here's a little trick. So what if I asked you here, oops, let's say instead, nope. Let's say instead I wanted this. Given that I saw a positive test result, what's the probability that someone is HIV negative? Given the work that I already did, how could I come up with this pretty quickly? So I had up here, given that I saw a positive test result, the probability that I actually had the disease was 0.38. So now I'm saying, given that I see a positive test result, what's the probability they don't have the disease? Yeah, 0.62. Because I said earlier when you condition on the same state of nature, but the same thing actually applies if you condition on the same outcome of the test. If I condition on the same outcome of the test, the conditional probabilities for the two different states of nature have to add up to 1. So 0.62. I think that intuitively makes sense. If I'm looking at my group of people who got a positive test result, what this is saying is 38% of them actually have HIV and 62% of them wouldn't have HIV. Any questions on that? No, I'm rushing a little bit since we lost some time, so make sure you ask questions or stop me if you have them, okay? All right, let's go. Try to work through one more example. So I had this kind of goofy example, but I think after we do it, it'll make a little more sense. So let's say that we're thinking about innocent or guilty people. So did I skip a slide here? No, I didn't. I'll just set this up with my words. So let's say we have this truth serum and we think that like this is going to be, someone developed it so that we could identify who's telling the truth and who's not, and identify, individuals who are guilty or not guilty of certain crimes. Okay? So our states of nature here, we can think about it as are innocent and guilty, right? Someone either is innocent or they're guilty. Those are our two states of nature. Given that someone's innocent, this truth serum makes them say that they're guilty 1% of the time. So essentially, we can think about it as there's kind of a false positive here, right? In the sense that innocent people are saying they're guilty incorrectly 1% of the time, but it means that the truth serum, kind of works and makes them say they're innocent 99% of the time. However, for guilty people, this truth serum, the people will still actually lie, right? The truth serum doesn't work, and the people say they're innocent 10% of the time. Okay? Now, that also means that if someone is guilty, the probability the truth serum makes them say they're guilty, it correctly kind of gets criminals to confess, which would be 90% of the time, right? We think about the other kind of outcome of the test here. So we're then kind of given this additional information that if all people kind of brought in and kind of questioned and given this truth serum, that actually only 5% of the suspects are guilty, okay? That, they question a lot of people, but that they only kind of bring in guilty people 95%, or the, percent of people out there who are committing this type of crime, it's only 5% of the population. Okay? So, and here I think I have a grammatical error. So 5% are guilty. Here, oops. Let's do this to make it a little bit better. I'll change the words here. So I was trying to give you that 5% of suspects are guilty. Then, if we see the truth serum indicates that someone's guilty, what's the probability that they're actually innocent? Right? So what we're thinking about there is, we've seen if the truth serum indicates guilty, so we're thinking about, given that this truth serum makes somebody say they're guilty, right? What's the probability that they're actually innocent? So what's the probability that they're actually innocent? That's what we're looking for, right? So here is our state of nature, and here is the outcome of the test that we see. We see that somebody confesses or says they're guilty after taking this truth serum. What's the probability they're actually innocent? Because we know this truth serum doesn't work 100% correctly, okay? So what we're going to do first is write down the probabilities we have now. These two were given to us pretty easily. I was kind of already written out for us here. I then said the probability that we see a guilty individual, or we could think about this as the probability that someone's guilty would just be that 5% or 0.05, which means coincidentally, we also know the probability that someone's innocent, right? The probability they're guilty is 0.05. What's the probability they're innocent? These are two states of nature. Those probabilities have to add up to 1, so 0.95. Yep. So we've got all of our kind of probabilities now laid out. Right, we've identified kind of what we were given, and then we just talked about how we find the probability they're guilty and how the probability they're innocent. we already said that what we're looking for is that given that the truth serum makes them say they're guilty, what's the probability they're actually innocent? So all we're going to do is use this idea that I know my state of nature and my outcome of the test. I'm just going to go back to that general form of the equation and write it out in the context of my example. Okay? So I'll go all the way back, just to kind of give you a, here we go. I'll go all the way back to this equation. I identified my state of nature and my outcome of the test. So then I'm just plugging things in here. Right? So my state of nature here, we were interested in if they were innocent. So I would just write innocent everywhere I saw state of nature 1. That means every time I see state of nature 2, what should I be writing in there? That the person is, 2 states of nature were innocent, and if I'm not innocent, I am guilty of a crime, right? So the other state of nature 2 here is guilty. And then the outcome of the test that we saw was that the truth serum made them say they're guilty. I'll wait till this, you got it. Come back. Screen's going out. Okay, here we go. So then state of nature 1, sorry, I talked about that. Sorry, outcome of the test E is that the truth serum makes them say they're guilty. So we just kind of write that in. And then we would have everything written out. In the context of our example, right? Well, now once we have that, what's the probability someone's innocent? 0.95. So we can plug that in here. Probability they're guilty, 0.05. Given that they're innocent, what's the probability the truth serum makes them say they're guilty? We had 0.01 there. Now here's where I don't actually have the last piece I'm missing, right? So I'm missing that once I plug all those values in, I'm still missing this last probability. However, I can find this because if I look at, have I conditioned on that same state of nature somewhere else? Well, sure enough, I have. So given that someone's guilty, the probability this truth serum makes them say they're innocent, it was 10% of the time. So given that they're guilty, then what would be the probability the truth serum makes them say they're guilty? It would just be the remaining 90%, right? Or that probability would be 1 minus that 0.1 or 0.9. And my box is a little off here, right? It's supposed to be kind of covering this, okay? So now I've got everything that I need. I guess it wasn't off, but I think it would have been better if I had put it over there. Now it's just a matter of kind of plugging this into our calculator, right? Now notice every single time we're doing this, this numerator is always the first component of the denominator. So that kind of always makes it a little bit easier if we're thinking about plugging those values in. And really what these represent is here's my group of people who are innocent, but the truth serum makes them say they're guilty. And then this other group of people over here, the second part of the denominator, is people who are guilty, and the truth serum made them say they're guilty. Okay? No, so it's just a matter of chugging those values into our calculator, and we'd end up with about 0.174. Okay? So, the reason why this is so high, given that the truth serum made them say they're guilty, what's the probability they're actually innocent? Well, that means like of the people that we find guilty, if we use this truth serum to put people in jail, 17% of people would actually be innocent. Okay? And I use this goofy truth serum example, but really, well, I'll come back to this. We really could think of this as a jury, right? I mean, this truth serum is essentially a jury in that I could just replace everywhere where I had truth serum before, I could put the word jury in, and this is like a direct corollary to what happens in the justice system, right? So, I could actually find, right, people who are, given that someone is actually guilty, what's the probability the jury finds them innocent? Given that someone's innocent, what's the probability the jury incorrectly finds them guilty? And I can kind of get an idea about those probabilities. I've never kind of went back and done enough of this work or kind of looked into who has. But, because we've had technological advances over time, there's been a lot of cases where we can go back and they get overturned, right? There's like the Innocent Project and stuff like that. So that you can actually kind of get an idea about, from those overturned cases or from those cases they went back and found DNA evidence that it was somebody else, we can get an idea about people who were actually innocent that a jury found guilty, right? We can also figure out, when juries made the wrong decision as well, right? When DNA evidence comes out and that when a jury found someone innocent, they actually should have been found them guilty. So based off this overturned court case data, you could actually get those probabilities, and then it's just like we did, but instead of saying, you know, what's the probability that someone's innocent given that the truth serum says they're guilty, what's the probability someone's innocent given that a jury found them guilty? Now, we hope that's not as high as 17%, right? Hopefully those probabilities, when we look at that, you know, overturned court case data, we don't find probabilities that high, but really be writing out, we'll wait 2 seconds, hope this comes back on. I think I'm at the end of my road with this thing. So I just basically have that same thing written out, but instead of truth serum, I have jury, right? You kind of think about, I think I meant to have these at a different time, right? People that are guilty, the jury found innocent. People that are innocent that the jury found guilty. I mean, we could argue these. I'm just using them as a cultural kind of example here. But, you know, this is a pretty real-world applicable thing, right? If we can use that overturned court case data to get an idea about these probabilities, we can start to make statements about the percent of people in jail who are actually innocent and the percent of like serial killers running around who are actually found. I shouldn't say serial killers, but criminals who are running around and innocent, right? Or sorry, running around who were found innocent but actually guilty. Okay? So some really direct applications of this Bayes theorem. Let's go back here. So I skipped over this slide. Really, it was just saying that, okay, if the truth serum, given that the truth serum made someone say they're guilty, what's the probability they're innocent? We said that was about 17%, or probably 0.17. So if the truth serum indicates guilty, so still conditioning on that same state of nature, what's the probability that the suspect is guilty, right? So if I'm thinking about writing out now what I'm looking for, I've got the probability that given this truth serum made them say they're guilty, what's the probability they're actually guilty? Well, we just found this up here was 0.174. We're conditioning on the same outcome of the test, looking for the different states of nature. So this conditional probability should just be 1 minus that, right? Now we could go ahead, rewrite Bayes' theorem in the context of this example and plug all of our values in. But because we had already found this, we should know that we could just subtract what we had just found from 1, right? Because we're still conditioning on the same outcome of the test, we're just looking for a different state of nature. So if we do subtract that from 1, we should get, what, 0.826? So I was kind of putting that question to allude to this idea that we can, if we condition on the same state of nature, sorry, the same outcome of the test, the 2 different states of nature, those probabilities should add to 1. But I already went through that with the previous example as well. All right, 2 minutes left. So we'll save this stuff for next class, but I want to go back something I glossed over, and I'll probably, I'll try to take some time on Tuesday to go over this. But you can also, when you're writing out these probabilities, you can write these out as a tree. So I have an example with the HIV one that we're thinking about, but I'll write one out for you in a more general context. So I'm just going to end class by switching over. Here we go. All right. So you can always start out is with a probability tree where you're looking at the probability of your first state of nature and the probability of your second state of nature, right? So you know this kind of row of your tree has to add up to 1, right? If I'm thinking about this. I then can think about over here on this state of nature, I can condition on that state of nature, right? State of nature 1 here. And I can just find the probability of the 2 outcomes of the test, right? And because I'm conditioning on the same state of nature, the probability of these 2 outcomes, right? If we add those up, these will add up to 1 as well. And then on my other branch here, I'm looking at my second state of nature. Kind of going to run out of room probably. But if I condition on that second state of nature, look at the outcome of that test, condition on that same state of nature, and look at the other outcome, right? These 2 parts of this branch have to add up to 1, right? So you can always write this out in the context of your example. What you start out with is the probabilities of the events themselves. Then whatever event you have here, write out your conditional probability on that event but for the two outcomes of the test. And then over here, you're conditioning on this branch's state of nature, but the two conditional probabilities for the two different outcomes of the test. Okay. Oops, so those add up to 1 as well. So I'll leave this kind of here. We're over by a minute, so I'll let you guys kind of get out of here. Like I said, I'll post that Excel video so that we'll have kind of the first half hour of the class that we missed. And I pray to God that we'll either won't have these issues or we'll be in a different classroom by Tuesday, okay? All right. We'll see you guys on Tuesday. I will get an online quiz up today. Should be pretty easy once I get back to my office. That'll be kind of related to some of the stuff that we talked about today. And that is due before we start class on Tuesday, okay? All right. Thank you for putting up with all this stuff today.